Today I'm going to tell you the gospel of process mining and predictive process monitoring in Apromore. This is all joint work with the University of Melbourne, and we are currently very eager to give this type of talks because as we speak we are trying to set up the company that will, the spin-off company that will commercialize Apromore. So Apromore is essentially a 10 years effort. It started by University of Tartu and Queensland University of Technology, where Marcelo La Rosa was, and it started as a process model repository. So it was about managing process models. Around 2013, we pivoted and we kind of decided to turn it into both a process model repository, but also a process mining platform. And over time, it has become more of a process mining platform, but that, because of the legacy, allows you to manipulate models and logs at the same level as if they were both first-class citizens. So the general context, of course, is business process management. So we are there to improve. We are here to, what we want is really to improve business processes. I always say everything is allowed except the killing, doing something illegal or unethical, and not improving business processes. Within the business process management life cycle, we focusing on business process monitoring, where I believe process mining and predictive process monitoring fit the most. We conceive process monitoring as consisting of two parts. Performance dashboards, of course, that allows you to monitor the performance of the processes in the organization in terms of performance indicators that talk to the business at different levels, operational, tactical, and strategic. And which are derived, of course, from transactions or events recorded in the databases of the company's enterprise information systems. And the second part, which is what I will focus today, is the process mining part, which goes beyond performance dashboards in the sense that it's not really focusing on performance measures, on numerical aggregates of performance, but it opens the box and it goes inside the process, into the activities, into the flows, into the decisions, to explain why the performance that we are observing is the one that we observe. So to explain what the performance measures are indicating to us. So we see these two things as being complementary. I'm going to focus on the process mining part, and our way of seeing the field is through the cross. So at the center of any process mining technique, you have an event log that is data that you extracted from an enterprise system, which contains transactions related to a given business process. And from there, you can do 4 types of operations. You can discover a process model from the event log, or if you have an event log and you have a process model, you can compare them effectively and check if the process model conforms to the event log or vice versa, if the observed reality coincides with what you have captured in your models. Sometimes you have 2 event logs. Imagine this is the event log of all the cases where the customer was happy, and you have a second event log with all the cases where the customer complained. And you need to understand what is the difference between the two. So you need to do what I would like to call discriminative process mining. Unfortunately, the professional community didn't adopt that term, but they rather call it variant analysis, where you try to look at 2 logs of 2 different variants of a process, and you try to, maybe they are corresponding to different levels of performance, and you try to understand what are the differences, because that might give you hints as to why some customers are complaining, for example. So you want to get a diagnosis. And we know that conformance checking and variant analysis are quite related. They both are about comparing, but conformance checking is about comparing a model against a log, and variance analysis is about comparing 2 logs, reality against reality for 2 variants. But the techniques are quite similar. And finally, and not the least, sometimes you have a process model and you have an event log, and you want to understand the performance of the process on top of the process model. And that is what usually people call performance mining or process performance mining. It's a little bit different from performance measurement, because in performance measurement you're usually interested in understanding the performance of the whole process, and in here you want to understand the performance of the process decomposed into activities with respect to a process model. But of course it's related also to performance dashboards. The market of process mining tools has evolved quite a lot in the past 10 years. It's a relatively young market, actually, if you think about it. 10 to 12 years. Yet it has matured pretty quickly with a clear market leader, Celonis, that has partnered with SAP, and they target like large organizations, of course, you know. So there are competitors of Celonis: Minit, Myvinio, ProcessGo, QPR, Signavio, which interestingly comes from the process modeling tools field and kind of understands that they have to get into this process mining part. They call it process intelligence. There are some lightweight tools that have been, some of which have been around for a while, like Disco, that allows you to, in a quick and dirty way on your desktop, just grab a log and analyze it and do something with it. And it's pretty good in small organizations or in guerrilla scenarios where you're in a corner of an organization, your boss doesn't want to hear about process mining, but you see the value of it, so you download Disco and you get around. And there are a bunch of open source tools, Prom being the oldest one, but also the one with the highest amount of legacy, so it's not very usable, not very user-friendly. There are the people around the R community and the Python community waking up and integrating process mining operations into Python and R libraries. And there is also, we want to think, Apromore, which has less legacy and takes this approach of models and logs as first-class citizens, and let's do operations on the two combined. I'm going to do a tour of Apromore. That's the whole purpose of this presentation, and if we are lucky and the gods of the demos are with us, with no preparation, out of the blue, I'll do a demo. So the first thing that you can do in Apromore is automated process discovery. And it can do automated process discovery the way existing commercial tools can, using process maps, which is basically the Markovian abstraction of an event log, where the nodes are tasks and the arcs is directly follows relation. This task is directly follows by that task. Very simple stuff that is very amenable for zoom in and zoom out operations, and is very efficient to implement. And that's why vendors love it. But we also do BPMN, process model discovery, that from the log we derive the process map, and from the process map plus some additional information that we can quickly extract from the log, we can derive a process model. And this is a field that people here in Leuven have been working for a very long time, and this is not going to come as a surprise. When you discover a process model, you don't want, what you're trying is to discover what is the process behind in a way that is understandable. But you don't have the process, you only have a log that represents some executions of that process. And if we assume that the recording is correct, you know, this log is inside the process. It captures what's happening in the process. Maybe incompletely, maybe only some traces, but it captures what is happening. So we can assume the log is inside the process that we're trying to observe, and we want to discover a model. But what happens is that you don't want to discover a model that only covers the log, because if you do, then you are not learning anything, you are not generalizing it. Most likely it's going to be fairly unreadable as well, because in the log there is a big portion that consists of exceptions or infrequent behavior. And therefore you probably don't want to discover it, because it will pollute your model with a lot of paths that are not very relevant and that make your model very difficult to understand. So a typical process discovery technique will try to discover a model that is inside the process or that covers the process, that reflects what the process is about, that captures as much as possible of the log as possible, but not everything, because you don't want the process model to have this infrequent behavior on it, which will make it too complex. So to measure how good the model you discover is with respect to a log, we can talk of what is the behavior that the model has that the log doesn't, this part here. That is, the more you have, you need to have some, but you shouldn't have too much. This part, we call it additional behavior. You want to make sure that that you capture as much as possible of the log, so you want to have like the highest portion of this area, and that's called fitness. And you want to also make sure that your model captures as much as possible of the process, but you will not capture everything, so you will be missing some bits here, and that's called lack of generalization. So the more you cover this, the better you generalize. The less you cover the red part, the more you have lack of generalization. So we measure these 3 dimensions, plus of course the complexity of the model. So, inspired by a previous effort that had been done at Leuven on benchmarking process discovery techniques, we developed a full benchmark consisting of purely real-life event logs, about half of them public and about half of them private. And we did a systematic literature review of the field, and we identified something like 120 different process discovery techniques, which is amazing. But we grouped them, and at the end it boiled down to around 18 classes, and we could bring it down to like 12 main classes of techniques. And we took representatives of each class for which there were implementations, and we assessed them in terms of these measures that I mentioned before: fitness, precision, combination of fitness and precision called F-score, and generalization, and of course model complexity. And we found at the end that the technique, if you care about F-score purely, the techniques that have highest F-scores are inductive minor, which is a technique that discovers only block structure process models; evolutionary tree minor, that also is a technique that discovers block structure process models and uses a genetic algorithm, so it's fairly slow. And split minor, which is a technique we developed a few years ago, which discovers not only block structure process model, but also some unstructured process models, while guaranteeing that the models it discovers are deadlock free. So it discovers some forms of unstructuredness, but not in a way that creates deadlocks. We also evaluated Fodina, which is a technique developed here, and it came out quite close as well, with the difference that Fodina did not always produce sound models, most of the time, but not always. We found that, on the other hand, inductive minor is pretty bad in terms of precision, so it generalizes too much. In a way, inductive minor is a best effort algorithm when it doesn't find the pattern in the data. It just says that everything can occur in the model. Tasks can occur in any order, any number of times, and because of that, it has a lot of behavior that is not there in the model. So it allows for behavior that is not there in the model, particularly when you confront it with real-life event logs that actually shows up, because there are very complex structures around. Split minor does not have that problem, and the evolutionary tree minor does produce simpler models than the others, while achieving high fitness and relatively okay precision. But of course, it depends on how much you want to wait, because you sometimes have to run it for around 2 hours, 3 hours, 4 hours to be able to get a reasonably okay solution. So it's not suitable for any inductive use, but potentially it could be suitable for some batch uses. We investigated, of course, what was behind the results using different examples, and we confirmed indeed that that's what is happening. Heuristics minor and derivatives, including Fodina, are actually quite good, and it's very not surprising they were so popular for a long time. But they cannot. They have a, when you confront them with real-life event logs, you get into semantic errors. So you have to combine them with some smart filtering techniques. And the inductive minor generalizes too much, and the split minor tries to strike a trade-off in between. Not surprisingly, the technique that we integrated into Apromore was split minor. So I'm going to show, to stop the presentation, I'm going to show a quick demo of Apromore. So Apromore is a web-based tool. We have deployed it in some cloud nodes, but that's just for demo purposes. Our intention is that you download it and you run it either on your desktop or on a server. We want it also to be very suitable for teaching, that you can put some event logs and you can get students to go and start playing with them on a server. It has the main entry point into Apromore is a workspace consisting of a file system where you can store both process models and event logs. So in the first place, Apromore is a process modeling tool. I can take any process model and I can just open it. In the version that I'm running here, it uses Signavio editor, the open source version of the Signavio editor, but it is currently being migrated to the Camunda BPMN.io library, which has a much better performance than what you saw here. So the newer version that is available already online, or might be available online in the coming weeks, has better performance. It uses a better editor behind. So you can open any process model as a file, and you can do everything you can do, pretty much everything you can do with a process modeling tool. You can start editing, you can start adding tasks, etc. It has all the look and feel of a process modeling editor. But in the same way I had a process model, I can have event logs. So here I have event logs taken from 40U data center. For example, one that is pretty nice in the sense that it's a real life log. It contains some complexity, but it's not like super large. It's a sepsis log. And when you open a log in Apromore, it just shows you the process map. Because that's the simplest thing to show. You can compute it instantly. And it annotates, it puts the frequencies in the arcs and in the nodes, and it annotates everything in the same way that you will see it in a commercial process mining tool. And you can do what you can do in a commercial process mining tool. Here the log comes filtered, meaning that only some of the arcs are being shown. You can show it unfiltered. Of course, the more you unfilter it, the more it becomes completely unreadable, even if you were to visually zoom inside. It's a complete mess. So usually you will choose the right level of abstraction where you are satisfied that this is what you want to observe. And then you can, with one click of a button, just turn this into a BPMN process model instantly, and you can start doing the same filtering operations as before. So you can see basically what this does is that it applies split minor to add the gateways into the process map in a certain way. So you have a process map at a level of abstraction you wanted, and the thing is just like adding the gateways on the spot. A split minor is a very fast algorithm, and the key of split minor, that's why it's called split minor, is that it actually only cares about discovering the splits. So when you have a task that has multiple outgoing arcs in the process map, it just looks in the neighborhood up to 2 hops maximum to determine what gateways it should put in between these tasks. So it's very amenable to this interactive application. I have no idea how I managed to close this thing. I just probably did a wrong click. You can then apply filters like you could in any commercial process mining tools. Filters means that I can retain only the cases that fulfill a given property. Like for example, only cases where a given activity called admission IO occurs. It gets rid of all the other cases, and then it will instantly trim the log and recompute the process map and the corresponding BPMN model for the filter event log. And you can find everything that all the types of filters at the level of filtering events, dropping events, or filtering entire traces, dropping traces that retain only traces that contain, for example, a given activity, and you can select one of the activities. If I pick a random one, most likely it will give me yeah, so it gives you a filter event log. And you can also, here I am visualizing the frequency in the edges and in the arcs, but I can also visualize the performance, for example, mean performance. So here you will see that the arcs and the nodes are annotated with minutes and days, and you can quickly see where the bottleneck is. We have an edge here, a waiting time between admission NC and leukocytes that is of about 2 days, and that's the bottleneck in this process. There are some other, perhaps other bottlenecks hanging around here. So you can do log animation as well and so on, just like you were using this code here. But you have a BPMN process model or a process map, whatever you want. You can even switch between the two. The other thing that Apromore can do is conformance checking. I give a BPMN model and event log, and it compares them. So it's, for us, conformance checking, in the literature, conformance checking has been treated as a problem of computing a number in many cases. So comparing how fitting the log is with respect to the model, or how precise it is, etc. For us, it is, conformance checking for us is about detecting and explaining or diagnosing the differences between a process model and an event log. The traditional technique for doing conformance checking, or let's say this, one of the most prevalent techniques in the literature for doing that is based on trace alignment, which means for every trace, I find the closest corresponding trace in the model, the trace that has the smallest triggering distance to the trace I have at hand, and I compute an alignment between the trace and the model, which means I show how should the trace in the log be adjusted so that it fits, it mimics a trace in the model. And that makes it that you get for one alignment consisting of what happens in the model and what happens in the log for every trace. And that's very difficult to visualize. So when we conceived the conformance checking for Apromore, we thought we needed something different. We kind of needed something, this is too low level, we needed something where we could detect not differences between a trace and a model, but detect difference between the behavior of the log and the behavior of the model. So we designed a technique that we call behavioral alignment. And behavioral alignment, what it does is that it computes a formal representation of the behavior of the model in the form of event structures. It computes a representation of the log in the form of an event structure, which is pretty lossless. And we kind of compare the behavior of the two. And when we see that the model can do something that the log cannot, we try to capture it in terms of a difference pattern. And we came up with a taxonomy of around 13 different types of differences, inspired by previous research on differences between process models. When you change a model, what kind of changes can you make? We came up with a similar taxonomy. And so when we can detect when we detect that the model can do something that the log cannot, or that the log can do something that the model cannot, we will classify it into these 13 patterns, and based on that, we will generate some form of diagnosis. So for example, in this model, I have this model and I have this log. I will detect that according to the model, I should always do checking from sources, i.e. task C, but as I can see here, there are traces here, down here, there are 2 of them where C does not occur. And therefore we will classify that as an optional task difference, and we will produce a statement effectively saying that task C is optional in the log, i.e. maybe skip the log, whereas it is compulsory in the model. We can also detect behavior that the model has that the log doesn't have. For example, here in the model I have this loopback with these 2 tasks, I and G, and in the model I never observe it. So we will detect that there is a whole loop that is observed in the model but not in the log. And as I said, the way we do it is that we take the model, we compute what we call an event structure of the model. So event structure is a technique for representing the behavior of systems with concurrency, so it's very suitable for a model. Normally, event structures can be infinite, but there exist techniques based on concepts of prefix unfoldings that allows you to represent behavior with cycles even finitely using an event structure. So we kind of use that to represent the behavior of the model in a way that we capture all the causality relations, like this task causes the other task, like it's like a directly follows. All the exclusion dependencies, like this task is exclusive with respect to that other task, there's a sort of XOR, and all the parallel dependencies, this task is parallel to the other. And because we capture all those relations, that is what allows us to produce statements like what you saw before, like in the log, there is this task is compulsory, in the model it is not, in the log these 2 tasks are exclusive, in the model they are in parallel. We can produce all those sorts of different statements as a result. We also take the event log and basically we compress the event log. It's a compression operator that just makes it smaller and that turns it also into a prime event structure. And then we compare the 2 prime event structures using typical techniques of the same type of techniques that you use to do a product of 2 automata. We just define a product of 2 event structures. That is error correcting, which means it doesn't assume that the model can always do mimic the moves of the log or vice versa. And when the log can do a move that the model cannot, then we mark it down and in the synchronized product, and we keep going. And we even implemented using an A-star algorithm, which ensures that we find the partially synchronized product with the smallest number of discrepancies, effectively. So the PSP that we produce is a minimal explanation of the discrepancies between the model and the log. Based on this synchronized product of the 2 event structures, then we can identify for every place in the event structure where the model moves and the log doesn't, or where the log moves and the model doesn't move, we can then classify it into these 13 patterns and that difference, and we emit a different statement accordingly. We also extended this in such a way that we can not only detect differences between the model and the log, like here there is a difference marked in red, but we can also repair the model so that the difference, the revised model does not have this difference between the model and the log. So I can go back to Apromore. I might have to log in again for some reason. Oh no, I'm fine. And I can pick an example of this is not a good thing because example. I have here a process model of a loan application, which is the one that I was using as a running example, and I have an event log that does not fully match the model, and I can call what we call the compare plugin in Apromore, and it detects that one is a model, one is a log, so it figures out that I want to do conformance checking. So it will then open the process model in the editor, and it will show me on the left the differences between the model and the log. In this case, there are 4 differences, which corresponds to 4 different patterns. And I can select one of the differences, and I can visualize it. I can see here that after check application is completed, normally, according to the model, I should do both the check credit history and the appraised property in parallel. And in parallel means that in principle, you should be able to do it in any order. But I observed that in the log, that's not true. You always do appraised property followed by check credit history. Perhaps more interesting is that sometimes, that's the second difference, sometimes I skip check credit history altogether, whereas according to the model, I should execute it. And so on, there are some other differences. And here I can apply the repair operation, and then I get a process model where it has been repaired. Well, you still have to get rid of the orphan thing, but that's made on purpose because this is a decision that the analyst has to do himself. And then it recomputes the remaining differences between the model and the log. As a result of this orphan task, it doesn't look very nice. Good. Feel free to interrupt and ask questions. Yes.
Ja, maar both Signavio and Camuna do the system modeling.
No, we haven't. We haven't. I was waiting for you to ask the question so that we can cooperate on that topic. But yes, we could do decision modeling in 2 ways. One of them is trivial. As part of the automated process discovery, we can discover the branching conditions in the form of decision tables. So if I have an XOR split, I can discover the branching logic as a decision table, and that will be straightforward application of existing decision mining techniques. So that will be one approach. I have another idea, though, on what to do there. What we probably want is not only to mine the decision, that's interesting from a descriptive perspective, but to do something that I would call decision optimization, which means that if you have an XOR split in the model and you are using certain business rules to do that decision, and you are able to refine that decision, so change the decision in a refined way, so that if you do the change, the performance of your process according to some performance measure will improve. Think, for example, that your performance measure could be something like processing time, which is effort, the cost, the human resource cost of the process. And you currently have a decision where you are escalating some cases. And you might find that if I escalate under different conditions, I can still achieve the same defect rate. If it's like you're trying to detect certain types of defects, you can achieve the same defect rate, but you can do it with less human cost because you are escalating less processes to the human actor, less cases to the human actor. So that can, in principle, be done by refining the condition that allows you to skip the escalation task in such a way that you do not increase certain defect rate on the end. So the cases that you are letting pass will not be defective, but and then you move less cases into the human actor. So that will be that's really something that is in our radar from a research perspective. From a development perspective, of course, discovering decision conditions in Apromore is on the backlog.
I also saw one of the manual options was rules. Can you include your own rules there on the left side?
My own what?
Your own rules for
patterns.
For patterns.
these difference patterns that are here. The types of patterns, no, we don't really. You will need to extend the algorithm for analyzing the PSP. But it is true that the 13th pattern is a catch-all pattern. It basically says that a task is inserted or a task is deleted, depending on which direction you take it. And it would be good indeed if we could avoid using the catch-all pattern at all, if we could allow like some extensibility that you could catch additional patterns if you wish. That would be pretty good. So Apromore can also do well, performance mining. We saw a glimpse of it because when we were seeing the process model, I showed that you can switch to performance view, and of course you can visualize different types of temporal performance measures. But it can also do variance analysis. And for Apromore, variance analysis is just another comparison operator. So you saw that in Apromore, in order to do conformance checking, I selected a mono analog and I compared it. But you can take a log analog and compare the two. Or you can discover two models, a model of one log, a model of another log. And if you're satisfied with them, you can compare the two models. So we can do model-to-model comparison, log-to-log comparison, or model-to-log comparison. And the feedback that you get is more or less the same. There are slight differences because logs are finite, models are infinite, and of course comparing infinite against finite or finite versus finite is kind of slightly different. But it's the same. The underlying techniques are the same. So we played the game of like, we designed this technique for conformance checking, and now we say we have an event structure of the log, an event structure of the model, we cross it. What about we have an event structure of the log and we have another event structure of another log and we cross them? What does it give? And it gave. And we developed a log delta analysis technique that way, and the same for model-to-log model comparison. In fact, we actually started with model-to-model comparison, which was one of the most difficult ones. So, examples. Compare. So this must be two very simple models, and I can compare them. And then if it's model-to-model comparison, obviously it's going to show me a model on the upper part and a model on the lower part. And it's going to show me that there are certain differences between these two models, and this could be automatically discovered models from an event log. And I can select the difference, and it will show me what is the prefix where the difference occurs. And it shows me what are the tasks that are affected by the change, in this case F and H. In here, you can see that to do F, you have to precede it by E and G2, and H by I, and here the precedence dependencies are different. H is not preceded by I, and F is not preceded by G2 and E. And that's pretty much what the text was saying. And I can also do log-to-log comparison, except that that's less visual, so I don't demo it, but it's less visual because you just get text, and you have to really go into the text to understand what is the difference. Because if you do log-to-log comparison, there is no more. So we do basically log-to-log comparison either by allowing users to discover models for every log and comparing the model, and that gives me a more visual comparison, at the expense that when I discover a model, I slightly generalize, so there is some potential inaccuracy that is introduced, or via log delta analysis that will produce me statements of the form like, in the first log, this task is repeated, and in the second one, it is not. Something along those lines. Just in passing, another thing that Apromore has is drift detection. So you can give an event log, and you have traces, events, and therefore traces that occur in certain chronological order. and it can detect that there is a point in the process where the behavior after that point in time is different from the behavior before the time. It can discover both sudden drift, where the change happened instantly, but also a gradual drift, where there was a previous version of the process, another version of the process, and in the middle there was a mixture of the two, because there were some cases still running on the old version and some cases running on the new version. And it does that in a rather straightforward way. So can I say that we have published several times the same paper? Because what we do simply is that we are going through the trace, through the stream, and we are computing from the log of the last, say, 2 months of a given time window. We are computing the set of runs or the event structure of the log and the one of the model, and we then simply test if these event structures will represent sets of runs, if they are statistically significantly different, and if they are, like according to some chi-square test, then we will declare that there has been a drift. So we pretty much spent 5 years realizing that all the operations that people had developed in process mining with different representations could be unified, that what you need is an operation that abstracts a model into a behavioral representation. That could be automata, but we prefer event structures because it represents parallelism directly. Whereas in automata, the parallelism is only implicitly represented. You take the log and you convert it into an event structure, and then you can do all sorts of things. You can do conformance checking, comparing the event structure of the model against that of the log. Delta analysis, log against log, or model against model. Or you can do drift detection. You are just maintaining the event structure at different times windows in a sliding window manner, and you are comparing the event structure of the period after a given reference point with the behavior of the period before. It's literally that. This is a log, this is a log. So what I'm doing is doing a comparison of the two. I just need to do it in a way that I can quantify know how many runs there are that are the same here and there and so on, so that I can run a chi-square test where it's about the same thing. And there are also, it is also possible to discover the process model from the event structure, except that automated process discovery is different from the other operations because you don't want to discover any model. You want to discover a model that filters out noise, that generalizes in a certain way, and therefore it is fundamentally heuristic as an operation, automated process discovery. It's not an exact operation like the other ones, but it's a very heuristic operation at the end of the day. And therefore, we did not pursue the avenue of discovering the process model from the event structure at the end. We said it's kind of, because you want models that are simple and you want to approximate on purpose, then it's better to start with a much simpler representation, and the EFG, of course, provide that simplicity. So that is the part of Apromore that deals with process mining in the classical way. Apromore does try to go beyond, and it covers also performance aspects, performance monitoring. It has, particularly in what concerns performance monitoring, Apromore focuses on predictive monitoring. Predictive monitoring means that you have like an enterprise system from which you can extract an event log, or from which you can stream events in real time. And predictive monitoring essentially takes this event log and builds a model that then, given a stream of events, allows you to produce effectively a stream of predictions, which tells you for every case what is going to happen to it in the near term. So we developed a set of techniques for doing this, and wrapped them initially around a tool that we were calling Nirrisati. It was a kind of a separate project relative to Apromore. and developed all the machine learning machinery for building the predictive models, all the event streaming facilities for generating predictions at real time, for processing events at real time, and turning them into dashboards, be them detailed dashboards that for every case tells you what is going to be the next task and so on, or aggregate dashboards, which tells you like for different types of products or for different customers, for example, how many cases are going to run late. Or more recently, we've been working also on this alarm-based monitoring. So what is, if users don't want to be seeing the predictions all the time, but just want to be warned when they need to intervene, they can optimize, define a policy, and there is the engine takes care of optimizing the generation of alarms with respect to the policy that the user has defined. In predictive monitoring, we have looked at the problem of predicting at a given state in a case what is going to be the next activity, when, what will be the timestamp of the next activity, when will it be performed, how long will the case finish take until completion, remaining cycle time. If you give me a labeling function, so you can define like some sort of predicate that given a completed trace tells me whether it's a good one or a bad one, which we call an outcome, we can then predict what will be the outcome of the case. Will the customer complain or not, for example? Is the or we can also, of course, predict numerical values. If we have to pay a compensation, how much we'll have to compensate. Or if we have an invoice, how much of it will be repaid, and so on. So for that, the general framework that we adopt is pretty straightforward. We take an event log, and by means of sequence encoding operations, we turn it into feature vectors. We turn every trace in the log into a feature vector that we use to train a classifier that, given a sample, allows us to predict an outcome, or allows us to predict the performance measures, or allows us to predict the remaining time. So the problems we kind of tackled was what kind of encodings are suitable to transform traces in an event log, like here trace C001, into a feature vector. And we came up with a taxonomy of such encodings, and we did a systematic comparison of them to see how they perform. One of them that turned out to be pretty good was what we call an index-based encoding, which is a lossless encoding. So one of the things we learned here is that it's better to go lossless first. So produce a feature vector that doesn't lose any information, and then let the classifier figure out what to do with it, than to produce a lossy encoding into a feature vector and then have the classifier basically feeding less information into the classifier, even though it looks very attractive at first glance because you have less features. But nowadays, if you have sufficiently large data sets, ensemble methods are really very good at automated feature selection. So they figure out what they need to take from the encoding. We also experimented with aggregation encodings, where for every attribute in the event log, we do a count. We count, for example, how many times an activity has, for each activity, how many times it has occurred, or for if you have a numerical value, like for example, the amount of the loan, you can do the sum or the maximum, the average, whatever. And we also worked with encodings in terms of recurrent neural networks, LSTM-based encodings, although that is not in Apromore. We also experimented with different approaches to what we call bucketing. The idea of bucketing that has been quite explored in the field of predictive process monitoring and in other fields is that instead of building one single classifier for all the traces in the log, you can build one classifier for different. Actually, you have to build the classifier for all possible prefixes in the log, because for any prefix you have to make a prediction, not only for completed traces. Actually, that's not interesting, but for any prefix you have to do a prediction. And instead of building a classifier that can classify any prefix, we can bucket them. The neutral approach is not to bucket, zero bucketing. You just create one classifier with all the traces. You can use clustering techniques, which means you just do trace clustering. We're going to hear a lot about trace clustering today. Pick your favorite trace clustering technique, and you cluster the traces into, say, 10 or 20 buckets. And for each of them, you create a classifier. At runtime, when you have a prefix of a trace, you find what is its closest bucket, and you use the classifier of that bucket. And the advantage is that every cluster contains similar prefixes, and that you can sometimes build classifiers that are better at predicting because it's taking homogeneous data as input as opposed to a lot of heterogeneity. And as well, prefix length clustering. Prefix length clustering means that we create one classifier for all prefixes of length 1, one for all prefixes of length 2, all prefixes of length 3, all prefixes of length 4. It's much stricter than clustering. Clustering does a little bit of it because naturally traces in a bucket will be of more or less the same length, and prefix length encoding is stricter. But prefix length encoding lets itself very nicely to be combined with index-based encoding, because if all your traces in your bucket are of size 4, and you have, let's say, 10 attributes, then you can encode all these prefixes of size 4 as features of size 40, or as vectors of 40 features. 10 features for the first event, 10 features for the second event, 10 features for the third event, 10 features for the fourth event. So all the traces in the same bucket can be encoded as a feature vector of the same size without having null values, which can sometimes mess around with the classifiers. And we conducted a systematic evaluation of all these techniques, and we kind of found that actually clustering techniques, if they are hyperparameter optimized to get so when you optimize the classifiers for the different clusters, you can also optimize the number of clusters, 2 clusters, 3 clusters, 4 clusters, etc. So in the same hyperparameter optimization round, you optimize the classifier and the number of clusters, all the parameters of the classifier plus the number of clustering. You can get very good results with clustering. It's very heavy computationally in terms of the processing power for training the model. You can get also pretty good results with aggregation or encoding, but it's more unreliable. Sometimes it works well, sometimes it doesn't. And you can also get, you generally get better results with index-based encoding probably because you are generating feature vectors that are in a lossless manner, and therefore you give more information to the classifier than you can when you do aggregation encoding or massless encoding, where you are basically trimming off information before giving it to the classifier. This has been integrated in Apromore. So it originally was a separate project called Nirnisati as a research project, which we finished, and we integrated this into Apromore. So in Apromore, you can give an event log, and there is an interface that allows you to train a classifier. And then you deploy this classifier into some Kafka infrastructure, and the Kafka is receiving streams of events, and every time it turns that into a stream of prefixes, and every time it receives a new prefix, it makes a prediction for it, and it pushes the corresponding prediction out, and this can be used then to generate dynamically updated dashboards, if you wish. And it can do prediction of outcomes, prediction of performance measures, particularly cycle times, and future events, next events, for example. I have to say that this part of the demo I didn't prepare it, so it's going to be completely improvised. So I'm already making an excuse for why it's not going to work. But let's try predictive monitoring. So I can take, for example, the same sepsis log, say something, sepsis train, and I can train a predictor, and that's going to open me up the prediction the training interface of Apromore's predictive monitoring component. which allows you to put in models, logs, and train a classifier either for the remaining time or for the next activity or for whether it will be fast or slow with respect to a given case duration. So, if, for example, will it take more than 5 days or less than 5 days? And it has some other options in there. It has an advanced mode where if you kind of understand all these concepts of encodings, bucketings, and prediction methods, you can configure what type of bucketing you want, what type of encoding you want, what type of classification technique you want to use. Although we have found quite systematically that XGBoost tends to outperform the other techniques in the vast majority of cases. We can train the model. Obviously, training the model takes some time. So I submit a job, and this is executed on the background, and training a model from a real-life event log, even though this is not that large, can take several minutes. From the larger events logs, it can take a couple of hours, depending on the parameters that you pick. So when it's ready, it will kind of notify you somewhere here, and you can validate it and see how it's performed. This was a very simple case, so I can see the accuracy of the classifier, which was for remaining time, in terms of mean absolute error for different prefix lengths, for different stages of the prefix. If I have trained the model, I can then I can deploy it and stream a flow into it, an event flow. So, for example, I should be able to take sepsis test. That was the previous log was the one split of the log for training purposes, and I kept the holdout for testing it, just for running a test on that classifier. So I can monitor and I can I can stream this log and make it go through a predictive monitor. So for example, I created this sepsis remaining time. We'll do this one. I can start streaming this. And in principle, is when it works. It then shows you a dashboard showing how the different events are arriving, and every time an event arrives, it will show you something like this for every case, whether it will be slow or not. What is the probability that this case will end up not on time? Of course, if it's above the deadline, that will be 100%. But then you can see the probabilities that different cases will finish at different points in time. And this is then being updated every time a new event comes in.
You start from a log, but you start from stochastic processing times for activities.
We start from a log, no metadata. So that was part of the philosophy that you have to give me metadata to define the outcome. If you want outcome prediction, you have to tell me, give me a function that given a completed trace tells me whether it was class A or class B, like normal or deviant, we call it. And that's about the only metadata that you need to give to the predictive monitoring, that you need to go and define it in some description file, some descriptor. Yeah, we tried not to, and we tried also to use preferably like more feature-oriented classification approaches, compute feature vector, then classify. We have worked also with generative models. I talked about the STMs, but also using BPMN model computed from the log, plus the branch probabilities extracted from the log and the processing times extracted to the log to also make predictions. We call that white box predictive process monitoring because you can see the predictions overlaid on top of the process model. So an automatically discovered process model, you can see I am in the current case in this task. These tasks remain. I predict that this will be the execution times. Hence, I predict that this will be the remaining time. So you kind of explain your predictions with respect to a process model. But it has a much lower accuracy to do that than to do a direct prediction. In fact, the very best technique, I don't have that slide here, but the very best technique to predict is a deep learning model, like a RNN with LSTM architecture, train it to predict directly the remaining time. So that's the most robust technique to do it. But it comes with the problems of needing some specialized hardware and so on to train in reasonable times. Yeah, unfortunately, I didn't carry the slides about predictive, about this benchmark of predictive monitoring methods. So to summarize, Apromore can do discovery from an event log, discover a process model, enhance that model with performance data, do conformance checking, generate performance report, or analyze differences between different sublogs or detect drifts, and you can do predictions. Next step for us is to, of course, spin off this commercially, and we kind of there are already there are already a few companies that have bought into Apromore. Bought into, it's free, it's all open source. So it's not buying, they just buy services, not the product. I see there are like two banks in Italy who are already using it, and there are also a couple of companies in Australia who have already deployed it, and there's like 2 or 3 ongoing projects in the field. So we hope there will be a lot more. It's also being used for teaching. The Apromore book is not yet coming, but is on the it's a project in the pipeline. But I you will need a very good classifier, a very good regression for that one, because I cannot. Yeah, but we are already using it like in several universities, of course, in Australia and in Tartu and in Rome. It's already being used, and we have already developed some teaching material available on the webpage. So if you are going to teach process mining, here you have finally the tool that can do, what the commercial tool can do, but it also allows you to show what the research tool can do. Because I always struggled with that, teaching predictive monitoring, that I kind of needed to show Disco or Celonis. But then I wanted to show like BPM and process discovery, etc. And then, doing with PROM was terrible because you're dealing with Petronets, and now you need to introduce Petronets to students just so that they understand the output. So then with Apromore we have addressed that problem. You can show like this is what the commercial tool does, and this is what you can do beyond the commercial tool with BPM and process models. So what's obsessing us now is something we call robotic process mining. Robotic process mining is analyzing now not event logs extracted from enterprise systems, but analyzing clickstream and keystroke logs, where you log everything that a worker is doing with their consent, of course, during a working session, during a whole afternoon, in terms of all clicks and keystrokes into Excel, into their mailing application, their email client, into their browser. So you log every click, every field that is selected, every field that is overridden, every value that is entered, every copying into a clipboard, pasting from the clipboard. You have the events at that level of very fine-grained atomic steps, and you want to discover not conceptual process models, because that will not be very useful, but you actually want to identify opportunities for automation. Like people often, they just start taking an Excel spreadsheet and they copied one row and they copied the first column into this field, the second column into that field, the third column that field, they submit, then they take the next row, they do a search, they copy paste items and they submit. And what we would like is like you just give me a recording of a whole afternoon of work and I can find you all the repetitive routines that you are doing together with the triggering context. And preferably in a way that I can generate a script out of it that I can execute on a robotic process automation tool like UiPath. That means tackling the challenge of discovering process specifications with variables, with data transformations in and out. And perhaps the biggest challenge is to discover deterministic routines. So you have a stream of these events, very fine-grained events, and you want to find conditions under which when this condition is fulfilled, I know 100% of your money back that the next thing you will do will be this, 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 and this, and this, and this. And I can deterministically capture it. So this concept of finding deterministic subsequences in a long sequences that contains not only events in the sense of like symbols, but also data attributes, payloads. So that's one of our obsessions. The other sort of obsession, maybe less obsessive, is how to make predictive process monitoring more explainable. You know, because one of the bottlenecks we see when we show predictive process monitoring in Apromore to potential customers is that they will not want to accept just that we are telling them this case is late or this case will take 10 days. They immediately want to know, so why are you telling me that it will take 10 days? What makes you make this prediction? Of course, that's a big problem in the field of data mining in general, but we are trying to look at what can we do from a process mining perspective, taking into account the specificities of the data structures we have as input. And the fact that we have process model, which is a big advantage. And then on top of the process models, we can do a lot of explanation. And how also to turn predictions into actions, that's what we call it prescriptive process monitoring as opposed to predictive. The simplest form of prescriptive process monitoring is alarm-based prescriptive process monitoring, where I just get streams of predictions and I determine when is the best time to launch an alarm in such a way as to optimize some utility function, taking into account that every time I escalate a case to a user, it consumes their time, to a worker, it consumes their time, so that's a cost. But if I do not escalate it, it can lead to a defect and a customer complaint, and that also costs something. So how can you train classifiers and tune classifiers in such a way that you can generate alarms optimally with respect to some objective function? And more generally, beyond alarm-based prescriptive monitoring, we would like to go into recommendation-based prescriptive process monitoring, where we recommend you, we will not only tell you there is a problem here, you should have a look at it, but we recommend you what to do in order to avoid that problem or prevent that problem. So that's what I wanted to tell you today.